The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, good morning, wherever you are in the country. It's Mark from SolidCAM. We'll begin our 30 minutes of free training for SolidCAM Live today. With me is Kevin Rankel. Hey, Kevin.
Hey, guys.
So today, we'll continue our kind of series of starting fresh on a part, and today we'll actually do some turning. So we have had some requests for turning. We haven't done too much turning since we started SolidCAM Live. So what we'll do with this is we'll start fresh on a purely turned part, and we'll cover a lot of the stuff that we've kind of touched base on a little bit over the years with some of our tips and tricks videos. I know we've done a lot of KevCam on turning. So we'll apply all of that fresh on a part like this to start. So let's just go and we'll do our beginning process here. We'll go Tools, SolidCAM, New, and I could choose between turning and mill turn. Since this part is only turning, I could do turning, but we always recommend that you use mill turn because it gives you the full functionality of the software. More specifically for just a purely turning part, it gives me the ability to add a Mac 2 for the second side, for the opposite side. Basically, if I took the part out of the jaws, flipped it around, put it back in, I could set that up in the same part file if I did mill turn. If I do turning, I think it only gives us the ability to add one Mac, right, Kevin?
Yep,
I think
that's correct. Yep, and where the big limitation comes is even though you guys may only have one spindle, but to take that part and flip it and put it back in there, you would always want to have, that's where that second Mac comes into factor.
Yeah. So I'll click mill turn, and it should open up a very similar window to what we normally see, and that is this first window here where you're choosing between external, internal, and if you choose internal, you're asking what name. In this case, I like to always give it something like SolidCAM Live for today. And then where we'd like to save it, I'll just save it in the same location I found the original SolidWorks file, and we'll be working in inch. So all of this is exactly the same as when you do a mill turn, a mill part, where you're choosing internal versus external, giving it a name, and where you'd like to save it. So if you'd like to get more of an explanation on that, you can review pretty much everything on the YouTube channel, because we talk about this one window a lot because it's actually pretty important for the creation of your file. But basically, it's exactly the same as we've always done with our other files. So I'll click the green check mark. It closes the original file, opens up the copy of it inside SolidCAM, relabels it design model, and now we can add all our definitions. And again, this window is the same window. It's very much the same definitions. What we're doing here, though, is we're going to set it up as if it's going on a lathe. So we'll start by choosing our post, very similar to what you do with the milling module. You just choose your post. In this case, though, because we choose the mill turn module, it gives me a list of my mill turn posts and my turning posts. So if I wanted to, I could choose just a pure turning post. I'm going to leave it as the mill turn because I think I have a machine sim on this, and we might want to look at that later. But essentially, you just choose your post, and it limits the types of toolpaths you can add to this file. So if we're in the mill turn module, but we're using a lathe post, we can only do turning operations or only do what that machine can do. So that also includes things like if there's a Y travel on this machine, the VMID associated with that post will let us know if we have the ability to move in Y, or if we do have the ability to move in Y, if we've exceeded the Y limits of this machine. So by choosing a post, you're not just choosing what post you want to use to output code, you're also reading from that VMID file the limits of the machine. Things like feeds and speeds as well. Next is coordinate system. So we're not going to talk too much about coordinate system only because it is done the exact same way as the milling side of things. The only difference is that in the place coordinate system origin 2, you definitely want to use your center of revolution face, because if this is going on a lathe, my origin is going to be dead center of the part. Now, I could use something like top center of the model, but you don't want to use that when you're doing a turn part, because you want this to be centered around the rotary of the part. If this part has any kind of revolved faces, that will give you the rotary center of the part. If you use top center of model box and you're doing a part that is going to be both turned and milled, maybe there's there's a flat or something that's going to move this to the top center of the model box a little further away from the center of the rotary. So that could be something that has maybe a revolved part to it, but then you've removed an entire chunk there. Remember that top center model box is basically the top center of the mathematical box, the outside edges of the part. That's not always going to be your rotary center. Whereas when you use center of revolution face, any cylindrical face I choose, it will place the z-axis dead center of that rotational face, like so. So my recommendation for turning, mill turn, use the center of revolution face. You'll get the dead center, the rotational center of your part, regardless of how many milled features or off centers or anything like that, eccentricities on your part. You'll always get the rotary center of your part. Now, it's not entirely necessary, but the way I was trained and the way I've been training people in my position as training manager here is I'm always telling people, if there's something you can locate on the part, for instance, here there's a keyway, I like to have the x-axis pointing towards that. I want that keyway at my 0 position, 0 degrees on my lathe or my mill turn, only because, for one, it's an easy thing to locate if you need to put this part back on the chuck, but also I don't want to have to index it to go doing that first feature. Let's say the first flat happens to be in this direction as well. I don't want to have to index the part every single time just to get to that one feature. That eliminates a couple of milliseconds in the cycle time, which could lead to hours in production. So if there's an individual feature that kind of locates it rotationally, I like to point the x-axis, x positive, at that. And to do that, very similar to what we did in milling, we'll just use the options over here. I'm going to do a flip around Z to get the X pointing at that keyway. Now, even if we're not doing the keyway on this part, this at least gives me the ability to kind of locate a rotational toolpath or any kind of thing relating to this part, relating it to how it would be set up on the machine. So even though we're not doing the keyway, if I'm planning on doing some engraving or something like that, this gives me at least some sort of reference point for an otherwise rotational part. So green check mark. Same sort of coordinate system levels, although here, since we're doing a rotational part, a revolved part, we now look at the radial levels as well. So you can look at all of that for your milling operations, but also for the radial, you're doing turning, so you can look at your radial as well. Click the green check mark. Okay, so Mac 1 position 1. And like we were just talking about, I can add a Mac 2 position 1 for backside. And again, I might want that to rotate like that.
And with some of your guys' post processors, this will be added automatically for you guys. So it all depends on the post and that sort of thing. So if this is something that you guys are commonly doing, always adding a Mac 1 and a Mac 2 for the front side and the back side, that can be set up in the post processor.
Also in your default SolidCAM settings as well, right?
Yes. Yep.
Okay. Okay, so stock. The stock and target definitions, again, are exactly the same windows as we saw on the milling side. The only difference here is it defaults to cylinder, because most likely that's the one you're going to use when you do turning. You could still bring in your 3D model, your STL file. You have all those options as well. If you really wanted to, you could probably bring in a box, but it's not really going to do anything different than cylinder, because what will happen after we click the green check mark, which we'll get to. But cylinder is the best one to use because it's a very default, very basic definition of what you're probably putting in the jaws. Probably just some bar stock or a cylindrical billet or something like that. So if it's just a purely revolved part, it's going to look like a cylinder when it gets spun anyway. So that's why I'm saying box versus cylinder, stick with cylinder. It's going to be spinning anyway. It's going to look like a cylinder anyway. And with cylinder, you get two options. You get relative to model and absolute coordinates. And they work exactly the same as the milling side. So relative to model, I'll click on the model. And under here, under offsets, in the positive Z direction, we're putting 50 thou. In the negative Z direction, we're adding 1 inch. Now, these are just default values, again, dictated by my SolidCAM settings. You can always go in there and change these. The only thing I would say is with the positive Z, if you plan on facing the front of that part, even if there's no material in real life, even if this is maybe just saw cut and you're just kind of cleaning up that face, you need to put some material in the positive Z direction, because what we'll see when we get to the toolpath is every single turning toolpath is a recognition toolpath, and it actually needs to see material that has to be removed in order to be able to be calculated. So if I don't put any material there, if I put a positive Z of 0 offset relative to model, I won't be able to put a facing operation because it's going to think that the stock is already on size. It's going to return an error that says something like toolpath is empty or can't calculate toolpath or something like that. So your turning toolpaths need to see some material to be removed. So I'm going to leave that 50 thou so we can see a couple of passes. But at minimum, I would say put in something there, even if it's maybe like 2/10 or something like that, just so that your finishing toolpath sees something that has to be removed. Externally, this is a radial value. So we're actually adding 100 thou radially on this part. And then internally, well, we're going to drill that out anyway. So I'm just going to leave that at 0. But I could put in my ID there as well, because whether it's relative to model or absolute coordinates, the internal diameter is the same number. It's either relative to 0 or it's the actual value of the ID. But if you're getting some stock that actually has an ID before you turn it, also I would say put that in, because as a recognition toolpath, you don't want it to be turning error if there's nothing there. So you can also put in whatever value represents that. Now, if we go to absolute coordinates, it's like it was in milling. These are now absolute values. For whatever reason, I guess they brought in the metric values. That's why we're looking at something that has a diameter of 50 inches there. But we're not turning that today. So let's go back to relative to model. I'll click on my solid there. We'll leave these default values there. Now, up until this point, it's very similar to milling. But what happens when I click the green check mark? It actually will spin that cylinder around the rotary axis and give me just the profile. Because as we're turning, we really only care about what this looks like on the top half, because all our tools are just engaging the material on the top half. So that's the only stock definition you'll see on screen. But when you do your solid verify and all that, you still see the full cylinder. If you do your machine sim, you still see the full cylinder. But for your turning, everything's just going to be related to this positive XZ plane. Let's go to target. Now, target, again, very similar. You just choose the solid that represents the final part. In this case, I just click on that solid. What's a little different here, though, is you now have the ability to generate a target profile. This profile is the geometry that will be used in your turning toolpath. So this basically will represent a cross-section of the part in the XZ plane, and you tell it how accurate you'd like it to be. So we actually have 2 modes to choose from, and then in one of these modes, there's 2 options. So let's go through that real quick. So in terms of modes, you have envelope and section. Envelope is what we're seeing as soon as I click the green check mark. It actually is going to give me that, again, that top half of the XZ plane as this part is spun around. So when you generate an envelope on a part that has some milled features, it actually takes that 3D model, spins it around the center axis, and gives us the outside profile of the turned part. So if there's any flats or anything like that, you won't see the flats in your turn profile. What you'll see is actually the outside diameter of that thing as it spins. So you never really need to do anything like configurations or anything like that with turning, unless it makes it easier to generate this envelope. But with a milled part, if there's some turned features to it, you don't have to bring in a turned version of the solid and then do a milling program on a milling part. You can actually do everything on that same part, and when you bring it into the turning modules, it will spin it around the rotary axis and gives you all the outside edges of the part. Does that make sense? Okay. If you want any clarification on that, just put a question in the question panel. But basically what this does is just revolves the part, regardless of the shape of the part, the status of the part, revolves it around the center axis and just gives us the outside contours of that part. Now, it actually can do that in 2 different ways. You can see here we have speed before accuracy and accuracy before speed. This was actually introduced either 2019 or 2020, I can't remember now, but basically what this does is it gives us the ability to increase the accuracy of that outside profile. So speed before accuracy, like you just saw, it basically just spun the part around, parses it, gives us the outside contour, and we're done. Accuracy before speed is a little longer of a calculation, a little longer of an analysis of the part, but you tend to get a more accurate representation of the turned profile. Let me give you an example of that. I'm going to bring up my whiteboard here just to quickly draw something, because I don't have the customer's part anymore. But during a training session last week, a customer had a profile that included a nicely circular groove. For some reason, my speed before accuracy generated a series of lines when it parsed that model. Now, you can still do your constant, your tangent propagation. It could have found all those lines for me in one click. I don't have to worry about choosing all the individual lines. But in the code, that's probably going to generate many lines of code just to do a simple arc. So what we did was we went back into his envelope. We switched it from speed before accuracy. We changed it to accuracy before speed. And what we got was a nice, smooth arc in the profile. So rather than parsing it and getting all these little lines, it analyzed it a little more specifically and found that that's just one simple arc. So that groove was one arc. His grooving operation was a single piece of geometry, and the code came out to be a nice couple of arcs instead of these little line movements. So your accuracy before speed can help you generate the target profile if you have difficult geometry. We've talked about this a little bit before, but if you're translating parts from a third-party format, step files, IGES files, parasolids, anything like that, sometimes the cross sections, the surface analysis, if you're doing HSS or HSM or any of that kind of stuff, sometimes the translation introduces some errors in the geometry. Inside SolidCAM, there are ways to account for that, different tolerances and that sort of thing. This is one of those things. This is one of those things we do inside SolidCAM that allows us to work with whatever geometry we have. So if we're trying to parse the model to get that turn profile and it's just coming out with bad angles or doesn't even calculate it nicely, there's something weird about it, this is one of the ways you can account for it. You just set it to accuracy before speed, and it actually takes a little more detailed look at it. I'm sure Kevin knows a little more specifically how it works about knurls or something like that, but bare bones, it's just a more detailed look at generating that profile, a little more specific to the geometry that you're trying to use. Section still gives you that XZ plane, but it actually is a pure section of the part. So in our case here, if I were to generate it, it actually will give me a cross-section of this part exactly at this plane. So it'll actually, instead of giving me this line here representing the internal diameter, it'll give me a line somewhere up here, giving me that top face of that keyway. So it actually gives us that cross-section. In addition to that, it actually gives me a profile on the bottom of the part as well. That can be useful if you are having trouble with the envelope. That could be useful if you're doing some negative X turning. Then you'll have some geometries you can choose there, and you'll have an X negative mounted tool. You can use that as well. Any reason why you would want to have top and bottom geometries, you can use that. If whatever reason somehow maybe you notice that the section lower half is generating better, you can use that geometry for many different things. All it really is the envelope does the revolution of the part. The section gives you just that direct cross section of the part. But let's go back with envelope. I'm just going to hit the red X, so we save the one we've done there. I'm going to use what generated there because it came out nicely. So in turning, that's it. We just need your post, your coordinate system, your stock, and your target. Click the green check mark, and we're ready to add toolpaths. So let's take a look at tools, tooling. So we'll go to our tool table. Now I chose the mill turn module. I have a mill turn post. That's why we still have the ability to add milling tools. But obviously for this part, we're not doing any milling. I'm not going to add any milling tools. We've done that enough with the series of videos we've done in SolidCAM Live. So let's talk only about the turning tools. So I'll say add turning tool. And you can see that there are two types. Unlike milling, there's actually two types of turning tools. Essentially what you're doing here is choosing the one that's either easier to define. There's always a way to just get something done and get going. Or maybe you have a custom tool that doesn't fit any of this top row. Let's go through these guys here, and then you'll see what these guys can do for you instead. So let's say we want to do a external turning tool. Well, in the composite tool definitions, all you're really doing is telling it what insert you're going to use and then what shank you're going to use. Let's define a very common insert in a very common shank. We'll go with the CNMG 432. So from the tables, I'm going to build with each line, each letter or number in the name, and then you'll see this actually change to reflect that name. So here's our C. We'll do our N. Here's the M. So CNMG already popping up there. 4, 3, So CMG 432. And that is also reflected if we look at the tool picture in our insert right there. Now, if I'm not actually intending to use a shank, or I'm going to bring in an STL model that represents my shank, my unique holder, I can check that box, and then I only have the insert. Or if I do have a standard shank, but for whatever reason I can't get it to define correctly and it's giving me collisions or anything, you can always just choose insert only and you'll still be able to generate your toolpath and it won't give you any collisions related to your shank. But obviously, if we're adding a shank, we're looking to see if there's any collisions or anything like that. So what we can do is we can go to the shank tab and then provide dimensions for the shank. So insert clamping, you have your options there. Insert shape, it's just going to take it from my definition that I just did. Lead angle, different options there. Very standardized definition of your tool. And that's because we're inside the composite tool. That's the purpose of it. It's supposed to be just whatever insert we're using, lead angle, different heights. And then you can see you got your M and N definitions there as well that you can play with. If we take a look at tool data, you can define it by inch per minute or inch per rev, RPM, or your surface foot. So it's very similar to the feeds and speed entry that you see in the milling side of things, just obviously with more specific units for turning. Holder, same thing as before. You can do your, well, actually in this case, your holder is a little more related to the fact that you're going to actually have a special holder to hold this in your turret. So this is where your STL creation skills will come in, because you're actually going to use the STL format to create your holders. Or if you're just bringing in a holder to hold the insert, it's still actually defined the exact same way. So for that, you can see our tips and trick video on our YouTube channel. Or if anyone has a unique holder they've been having trouble with, later on in today's class, we're going to give you my email. You can send me your part if you want to see how we can define that for use in turning. Okay, so let's now add from the second row here, the solid tools. In solid tools, it's a little more detailed. If we do an external roughing tool, you can see that it gives us a lot more detail here to put in, a lot more dimensions to add. This is very complex. This is not a definition of the insert. This is actually a definition of the profile of the tool. This is a little extra work, but this can come in handy if you're using a custom turning tool. Or maybe it's a standard tool, but it has maybe a ground relief angle or some sort of other customization. This could be for whatever you need it to be that is not covered by the composite tools. So there are oftentimes customers are using the composite tools and they never even touch this section here. But there is always that unique tool that you're eventually going to have to use for grooving or whatnot, and your solid tool definitions will come in handy. Let's do a save and exit. And let's use that first tool for some toolpaths here. So like always, you can always come up to SolidCAM turning and all your turning operations are up here. But Kevin and I, we're a little too old school. We'll keep going over here, right click and add turning operation. We can see the whole list here. So let's start with facing the part. And again, you'll hear me say it a lot when we talk about turning, but it's very similar to milling. The operation manager workflow is exactly the same. There's geometry, there's tool, levels, technology, and link. Those sections are always the same. We'll go through how they're a little different for the turning side of things, but essentially they are the same idea. You're defining, in this case, our geometry. In turning, we can choose between wireframe geometries and solid geometries. Wireframe is using that profile we just generated, and it's actually the easiest way, in my opinion, to program your turning operations, because you'll see exactly where you want the tool to go. It's just going to follow those lines there. With solid, you're actually choosing the faces to define the turning tool path. So I can actually say things like, let's just start with solid here. For facing, I'll have to say, I'm going to start at this face and then end at this face, and then click the green check mark to generate that chain. And then it generates the chain there. If I were to do turning, I would say starting from this face, going to this face, and then it would actually do the cross section of the solid through those faces to give me that contour. It's a good way to get associativity. It's a good way to use the ability of configurations and synchronization. If you check out my video on that, that's exactly what I use the solid-based geometry for. But for simple turning, I like to use wireframe. It's the easiest one. So we'll just go wireframe, new. You'll see that it's the same chain selection window that we always see when we do pocket and profile, and that's by design. It works the same way as those same toolpaths. In this case, though, I'm only looking at choosing from my target profile. So I'm going to do facing. I'm just going to grab this one line right here. That's the cutting direction I want to go in. I'll just click the green check mark and accept that. Well, you'll notice that line is not long enough to do my entire stock, but that's okay because inside turning, there's always this modify geometry button. I'm going to click on that. It'll auto default to extending to the start of the stock. So from that line that I chose, it's actually extending it to the start of the stock. And because I know I haven't drilled that or there's some material there or whatever reason, I'll just say auto extend to the end of the stock in that same direction, that tangential direction. So that one little line represents that entire face, and now I've got it to actually turn that entire face. Click the green check mark, and I've accepted that as my geometry. So you'll find a lot in turning that your turn profile, your target profile gives you a chain that is not for the entire part, but there's auto extensions and there's ways to modify that so that you actually can turn a little bit more, maybe even account for corner radiuses in your inserts, that sort of thing. In this case though, that line there just represents the Z coordinate that I want to face to when I do this operation. When I go to tool, I'll just go to select. From my tool table, I'm just going to grab my tool 1. Tool 1 doesn't seem to be oriented correctly, and I can double check that by clicking on this icon here, adding it to my mouse, and that's actually not how I want it to sit in the machine. So depending on your, I believe it's on the post or the VMID, you either have this section here where you can tell it, no, I want to mount it like that. So now it's mounted correctly there, or you would just go back into your tool table, and then top right corner, you'll click on mounting. And here is my machine sim. Actually, in this machine, the reason I have it in the operation level is because this thing actually has that swiveling head. You can kind of see it up there. So on this machine, the DMU, it actually has the ability to angle that head. So I can tell it with this one operation what angle I'd like it to take. But if you had just a very basic single spindle, single turret machine, then in this operation window, or the tool table window, you actually would have the ability to tell it how it's mounted in either positive Z, negative Z, positive X, or negative X. So let's get out of here. In this operation, we'll mount it that way, like that. And feeds and speeds, again, like always. On the operation side of things, you can plug in specific feeds and speeds for what you'd like this tool to do. Levels. In turning, your levels are just the safety distance. You can just tell it how far you like it to retract away from the updated stock before it does any movement. That's all that levels does in turning. Everything else about the turning operation is going to be controlled in the technology section. So in this case, we're doing facing. So we'll face the front or the back. So we tell it where we'd like it to do, what part of the part we'd like it to do. The working area for facing can actually be defined either by the stock, the updated stock, or by an extension of the target. This is very similar here to clear offset in your profile toolpath. You actually tell it how much away from that chain you like it to start turning, and then it'll just assume that that's the material that has to be removed. Otherwise, if you click on stock, it actually will define the toolpath by the updated stock. It'll actually trim the toolpath so it eliminates turning of air. Direction, one way or zigzag. That's up to you if your insert can handle it. Rough type, smooth or stairs, you don't really see it in facing. We'll take a look at this when we get into turning, but basically it's just a matter of, does it follow the exact contour that you've selected, or does it just do simple passes? But we'll take a look at that when we do turning. Step over, what you imagine it is, it's basically just with each turn, each pass, how much material it takes. We're telling it to do roughing, so we're going to leave some material in the Z direction of 8 thou. Retreat distance, we tell it how much we'd like it to retract before it repeats the next pass. If you use cycles in your post, you can just check the box that says cycles. It'll generate the cycle. With this same tool, I'm leaving 8 thou. I probably want to do a finishing pass. I'll just click on finish. And very much like we see everywhere else in SolidCAM, as soon as we check finish, we have the ability to add our compensation. Under link, very similar to milling, link is just your approach points, your ramping, your lead in, lead out. For turning, since this thing is already starting off of the part with that safety distance, I'm not adding a lead in, lead out, but I am getting it to start from the top right safety corner, and that is by default. By default as well, if you have a sub spindle and you're working on the sub spindle and you tell it something like facing of the back, this should actually default to top left safety corner. So if I were to do turning of the back, left safety corner would be something over here, so it knows to start closer to the part over there. But we'll go over here, save and calculate. Let's take a look at that with our special turning view. You can see that I left 50 thou there. We have 40 thou depth of or step overs. So there's one pass, another pass, and then the finishing pass. Okay, and then the red ball represents that top right safety corner. So any questions on that?
The turning, the turning side of things, we've got a lot quieter in the crowd now.
They're captivated by turning. That's why. Okay, so we're pretty much at the end. I want to spend more time on the turning operation. So what I'm going to do is I'm just going to take a step back and let's talk about fixturing for a second here. So in the machine setup is always required whether you're doing milling or turning. But in turning, it actually adds a little bit of an additional functionality, but it also is different in how you set up your fixturing. So let's talk about that real quick. So normally in your machine setup, you would come over here, you would say fixture none. You would just go to the three dots, and then you would choose the solid on screen that represents your fixture. In turning, we actually have three types of definition. Fixture 3D model is what you're familiar with. You would choose the 3D model on screen that represents your fixture. You'd give it a fixture mounting coordinate system and a part mounting coordinate system, and then that would be your fixture definition. You could do collision detection against that. You can tell it where it's sitting relative to your machine zero for things like 5-axis, if your mill turn has 5-axis, any of that kind of stuff. But in turning, we actually have these two additional types. Chuck standard is basically what you see over here. It's a three-step chuck. You tell it where on the chuck you want to hold this thing. So if it's a larger diameter, you're probably holding it maybe like that. So you can see the reference point is on the inside of that first step. If we're doing it on this side, that becomes a reference point right there. These graphics here tell you where the jaws are holding it and what the reference point would be. You tell it where it's sitting in terms of diameter over here, and it defaults to the diameter of the stock. So right now, I can tell that the diameter of the stock happens to just be 3.7. I didn't know that. You saw that we did it as relative to model, but if you actually had put in your definite size using absolute coordinates, then this number here should match that number. If you wanted to change where this is being held, let's say once we start doing side 2, and I want to hold it maybe on that diameter, all you have to do is just highlight this number, either plug in the number, again, if you know what the number is, or you can use the geometry to drive everything. You highlight that number, click on a piece of geometry, and you can see that it shifts to that diameter there. I'll just move it back by doing the same thing. Okay. Now you'll notice there is no axial position here. We're going to talk about that as soon as we exit out of this window. But in previous versions of SolidCAM, both the diameter location and the axial location were in this one window. Currently, they are not, and there's a reason for that. Let's go down to chuck or jaw parameters. So this is basically just the width and height of each step, width and height of the overall jaws. I'm just going to make this something a little more robust looking, a little bigger. And this profile here is simply just a sketch. It's just a profile generated by SolidCAM. Down here, we actually give it some thickness. So that thickness right there doesn't get represented on this window, but when you go to do your solid verify or your machine simulation, that's actually the thickness of the jaw. So to actually give this profile kind of a little bit of a thickness for representation purposes, this profile represents the mid plane. So that thickness is really just going to be the overall thickness, but in reality, it's going to be 200 thou in one direction, 200 thou in the other direction. And also, we're only looking at one profile. You tell it how many jaws you actually want down here. Let's click the green check mark. So that clamping fixture was added to our part. Let me just click on this green check mark here. The jaws, they actually sit right on the zero face because I have this all set to 0 here. If I regulate this using my mouse, you can see that I'm bringing that up by that much. So basically, I can type in a number in here. So for whatever reason, if I brought in a jaw that doesn't sit right on 0, maybe I've got some sort of whole fixture there or something, and I actually want that to be spaced a little bit, I have the ability to plug in a number in there, and that spaces the jaws away from there. But let's say we put this back to 0, just so that it looks like that. But that is where the jaws sit relative to the table. Now, where does the part sit relative to the jaws? Well, that's the indent section here, and I can highlight this number and change that number as well, or I can click on this icon right here and actually pick it from the solid. So the reference point of my jaws, I've got one inch of material here. Maybe I'll just put the reference point on that Z coordinate there. Click on that, click the green check mark, and now you can see that it shifts the part in the jaws axially by that much. So I mentioned before that in previous versions of SolidCAM, the diameter and the axial position of the jaws were in one window. Now it's here. So this gives you the ability to define your fixture once and then give it different axial positions depending on how you're going to use it. There's also this little guy over here. I don't see too many people using that, but that actually gives us the ability to rotate the part in the jaws as well, if that would make sense. Okay, so that part is now set up in my machine sim, as you see here. It's actually set up as my fixture. I just click OK, and that's it. That's it for the fixture definition. But there was that third definition that I wanted to cover, and if there's not much to it, that's why I'm saving it for last. But basically, if we made a new one, the third option is all of this, but to your own sketch. So you would draw inside SolidWorks a cross-section sketch of what your soft jaws would look like, and then you can do the same thing. You can give it some thickness, and you can tell it how many of those jaws there are. But you're using a sketch in this case, placed on your target profile as it should be mounted, and then that will become your custom chuck definition. So it's not a 3D model, it's just a sketch, but you still have the ability to define your soft jaws in however you like. Okay, but we'll save the turning, the grooving, we'll even do some threading on this part, maybe even some drilling on the middle there. We'll save that for the follow-up classes. So we'll continue with this part for the rest of the week, maybe even next week, depending on what we do on this part. So we'll do start to end on this part. I need to get something to drink, so I'm starting to mumble a little bit. So what we'll do is we'll end it here. If you have any questions, Kevin's going to put my email in the chat section. Send me any questions you have, any topics you'd like covered, any questions on this or anything else that we can cover for you. Obviously, this is for you guys. We know how to use the software, so we don't need to be here. But you guys have questions. We want you to learn how to use the software. So any questions at all, even if they're quick questions, we can cover them real quick before we continue on this part. So any questions at all, any topics at all that you'd like covered, please use that email to send me the questions. If you have parts you'd like to see done from start to finish, or if you've already programmed the part and you'd like to see how else we could do it for you, or to refine some of your toolpaths, very similar to what we did yesterday. You can send those parts as well if we're allowed to show them in a YouTube video. If you know anybody that can benefit from SolidCAM, please send them to us or give us their contact info. We'll contact them, and you will get a $100 gift card for that, $100 Visa gift card, just for letting us know that your friend is interested in SolidCAM. They get into a demo. If they do the demo, you get the $100. If it goes to sale, you get that 20% of the sale price. You actually get a finder's fee through that whole cycle of selling SolidCAM and VentureCAM if that happens. We will continue this till the end of June, every day at 2 p.m. Eastern time. So we'll see you guys tomorrow. Stay safe, keep your family safe, keep busy, and we'll talk to you tomorrow.
Have a good day, everyone.